Now when I proceed from left hand side, support A, at support A, RA is acting upward. It should be shown by vertical line above this reference line. Okay, so 12.5 kilonewton. This is the magnitude of the shear force. From A to C, no load is acting. The shear force remains horizontal, hence it should be shown by a horizontal line. So once I reach point C, 5 kilonewton is acting downward. So 12.5 minus 5, which is nothing but 7.5 kilonewton. From C to D, no load is acting. So shear force remains constant. That is 7.5 kilonewton. As you reach the point D, 15 kilonewton is acting downward. So 7.5 minus 15, you will get minus 7.5, which must be marked below this baseline because negative values must be plotted below this baseline or reference line. So now this is 7.5, that is minus 7.5. So 7.5 plus 7.5, which is equal to 15 kilonewton. So from D to E again, no load, the shear force remains constant. Okay, so 7.5. So once you reach the point E, 5 kilonewton is acting downward. Remember, you're proceeding from left hand side, so downward is negative. So already you have minus 7.5. So minus 7.5 minus 5, which is nothing but minus 12.5. Between E and B, no load, so the shear force remains constant, which is nothing but minus 12.5. Now, when you try to proceed from right hand side, for example, from right hand side, upward is negative, which is nothing but this magnitude equal to RB, that is 12.5. So minus 12.5 is the shear force at support B. So let's complete the diagram. So this is the positive shear force values and this is the negative shear force values. Now, how to plot the bending moment diagram? As we all know that bending moment is always zero at the simply supported ends. That is, here the bending moment is zero, here the bending moment is zero. Okay. Then how to obtain the bending moment at C? Okay. So moment is nothing but force into perpendicular distance. At C, I want to calculate the moment. So 12.5 into 1, that would be the bending moment at C. That is 12.5 kilonewton meter. And the nature of the bending moment diagram is a triangular lines for point loads, that is concentrated loads. Now, what would be the bending moment at D? Okay, I'm proceeding from left hand side, so clockwise is positive, anti-clockwise is negative. So 12.5 into 3 clockwise, so positive, minus this 5 gives anti-clockwise, so minus. So 5 into 2, okay, 5 into 2, that would be the bending moment at D. I repeat, 12.5 into 3 minus 5 into 2, that is the bending moment at D, which is coming out to be 27.5 kilonewton meter. Okay, since the loading is symmetric, you would get the same value on the other side also, same bending moment values on the right hand side also. Now when you proceed from right hand side also, here the bending moment is zero. So the bending moment at E would be right hand side anti-clockwise. This 12.5 gives anti-clockwise with respect to E. So right hand side anti-clockwise is positive, 12.5 into 1, which is nothing but 12.5 kilonewton meter. Okay, so now again same way, if you just calculate the bending moment at D from the right hand side, so 12.5 into 3 anti-clockwise positive and 5 into 2 clockwise negative, you will get the same value. This is one way of checking, cross checking the answer, 27.5 kilonewton meter, which is a positive bending moment. So without writing any equation or expression, you can calculate all these values in the calculator itself. Then you can write it on a paper. Okay. Next, we'll go to the next problem. Okay, so which shows a combination of the point load and uniformly distributed loads. Okay, the question will be like draw shear force and bending moment diagram. Okay, so it is understood that you need to calculate the unknown support reactions. Then you have to proceed with calculating the shear flow values and bending moment values, followed by the plotting the shear force and bending moment diagrams. In some problems, you may ask you to determine the location of maximum bending moment and also determine the magnitude of maximum bending moment. Okay, so that also we are going to see now. Okay, so here it is subjected to 5 kilonewton point load and a UDL of 2 kilonewton per meter, which runs over a length of 3 meters from the right hand support. Okay, so now we have to find out the support reactions R and R at A and B, that is RA and RB, by writing the static equilibrium equations. Sigma MA is equal to 0. So static equilibrium equations sign conventions: clockwise positive, anti-clockwise negative, 5 into 1 and plus 2 into 3, that is run length, UDL run length, 2 into 3, which is nothing but 6 kilonewton acting at a distance of 3 by 2, that is 2 into 3 becomes a point load acting at a distance of off of this, okay. So 3 plus 1.5, that would be the perpendicular distance or moment arm. 2 into 3 becomes a point load that is acting at a distance of 1.5, 1.5. So I'm taking moment with respect to A. So 2 into 3 is 6 kilonewton acting at a distance here. So 3 plus 1.5 would be the moment arm, which gives clockwise moment positive with respect to a reference point A, and RB into 6 gives anti-clockwise, so negative with respect to A. So we get RB to be 5.33 kilonewton, 5.33 kilonewton actually. Now, how to find RA? Sigma Fy is equal to 0. RA is acting upward positive and RB is acting upward positive. 5 is acting downward, so minus 5. And 2 into 3, UDL multiplied by run length gives you the load acting downward, 2 into 3, that is negative. So RB is known, so RA is 5.67 kilonewton. So by knowing these values RA and RB, we can plot the, or we can go for calculate the various shear flow values along the span of the beam, followed by plotting the shear force diagram. Okay, so this is the baseline reference line, which is understood that this line is, on this line the shear force value is 0 on the top, positive values, and at the bottom negative values of shear force will be plotted. Okay, so RA at A, RA 5.67 is acting upward, so 5.67 acting upward, shown by a vertical line. A and C, between A and C no load, so shear force remains constant. Once you reach a point C, 5 kilonewton is acting downward, so 5.67 minus 5, that would be 0.67 kilonewton. Again, between C and D there is no load, so this 0.67 kilonewton shear force remains constant. Now let us proceed from the right hand side. Okay, between D and B we are having the UDL. Okay, don't bother about that. Now let us start the procedure from right hand side. RB 5.33 kilonewton, okay, acting upward. So from the right hand side, upward is negative, so 5.33 kilonewton must be marked below the reference line, okay, below the reference line. So this is a minus 5.33 kilonewton is the shear force at B, and plus 0.67 kilonewton is the shear force at D. So between D and B, you have a UDL, uniformly distributed load, okay, and there is no any discontinuity or no any other load is acting between D and B, so that we can simply connect the shear flow values between D and B by a straight line, because the nature of the bending moment, sorry, shear force diagram for UDL is a triangle in nature or triangular shape. Okay, so positive values and negative values. Got it? So here the shear force is 0. So you can see here the shear force is 0, which means that bending moment is maximum, that we need to understand. Okay. Now let us come to this bending moment diagram. Okay, bending moment diagram. So how to find the bending moment at C? So we know that the bending moment at the simply supported ends are 0. So 0, 0 here. And 5.67 into 1, that would be the bending moment at C. Okay, so 5.67 kilonewton meter. Okay, then what would be the bending moment at D? At D, how will you calculate 5.67 into 3 clockwise, and this 5 gives with respect to D anti-clockwise. So 5.67 into 3 minus 5 into 2, that gives 7.01 kilonewton meter at D. This is the bending moment. Okay, so that should be uh, shown by a straight line. Okay, straight line. Now here the shear force is zero. Please remember that you have a bending moment value here, okay, which should be more than or greater than the 7.01 kilonewton meter that you need to remember. Okay, so shear force is zero. How to obtain this location? Okay, this zero shear force location occurs between uh, D and B. That is, if you're trying to calculate the location of this zero shear force from the support B, okay, and that location value must be less than 3 meter. Okay, that we need to remember in our mind. Now let us consider some section, okay, XX at a distance x from the right hand support. Now let us try to write down the shear force expression, shear force expression about this section XX by considering all the forces to the right side of the section XX. Okay, SF at XX, okay, right side upward is negative, so minus 5.33, and UDL is acting downward, so positive. So 2 is UDL multiplied by the run length, Newton per meter into meter, Newton. So 2 into run length is x. So equate this equation to 0, you get, after simplification, x is equal to 2.665 meter from the right hand support B. So at a distance of 2.665 meter from the right hand support B, the shear force is 0, which means that the bending moment is maximum. So how to obtain this maximum bending moment? Okay, so we have shown this distance here on the figure. So we have to write down the bending moment expression about xx. So write down the bending moment expression about xx considering the right hand side. 5.33 into x, right side anti-clockwise positive, and this UDL gives clockwise moment with respect to this section, so negative. So 2 into x, Newton per meter into meter, which becomes Newton. So 2 into x becomes the point load, which is acting at a distance of x by 2, x by 2. So 2 into x by 2, so x by 2. Okay, so this is the bending moment expression about the section xx. So if you substitute the value of x is equal to 2.665 meter in this expression, you will get maximum bending moment, which is coming out to be 7.1 kilonewton meter. Okay, so here you will get the 7.1 kilonewton meter, and the nature of the bending moment diagram from D to B is a parabola. Okay, it's a parabola. Okay, it's a parabola. It's not a straight line. So it's a parabola, and this is the value of maximum bending moment, and this is the location of maximum bending moment. Okay, so it's very simple. If you solve too many problems as homework, you'll be able to understand more detail. Then let us go to the next problem. Okay, so complete UDL. Okay, so on the top of it you have 2 point loads. Okay, 5 kilonewton and 20 kilonewton acting at the same distance of 1 meter on either side of the support. Okay, so here the loading is not symmetric. Okay, so because 5 kilonewton, 20 kilonewton are the two different point loads. Okay, suppose if instead of 20 kilonewton, if you have 5 kilonewton, means we can say the loading is symmetric. Simply we can sum up all the external loads divided by 2, you will get the support reactions. But here 5 kilonewton is acting at a distance of 1 meter from the left hand support, and 20 kilonewton is acting at a distance of 1 meter from the right hand support, and 2 kilonewton per meter UDL is uniformly distributed over the entire span of the beam. Then how to find out the support reactions? Let us take a moment about A. Okay, 5 into 1 clockwise is positive, anti-clockwise negative. We have to remember the sign convention. And 20 into 4, okay, plus 20 into 4, and 2 into complete run length 5 into 2.5, where that point load is acting, okay, 2.5, RB into 5, anti-clockwise negative. So RB is equal to 22 kilonewton. Then sigma Fy is equal to 0, RA plus RB acting upward positive, minus 5 minus 20 minus 2 into 5, that is kilonewton per meter into meter. Okay, so 2 into 5. So from this we get Ra to be 13 kilonewton. Ra to be 13 kilonewton. So once Ra, Rb is known, we can go for finding the shear flow values and plotting the shear force diagram. Let us plot the shear force diagram. Ra upward 13 kilonewton shown by a vertical line. And you remember between A and C, you have a UDL. Okay, the nature of the shear force diagram should be a triangle line. That is inclined line. It should be inclined line. Okay, that you should keep in mind. So 13 kilonewton is a shear force at A. Then between A and C, you have a UDL of 2 kilonewton per meter for a span of or over a length of 1 meter. Okay. It is distributed over the entire length. Why I am considering only the 1 meter means after 1 meter or at the end of 1 meter, you have a 5 kilonewton point load is acting. So it is required to calculate the shear force at C. Okay. So 13 kilonewton is the shear force at A. Okay, upward, and this UDL is acting downward. So 2 is the UDL, run length is 1. So 2 into 1, 2 kilonewton. Okay. So 13 kilonewton, UDL is acting downward. So 13 kilonewton minus 2, that would be the shear force at C. Okay. That would be the shear force at C, 11 kilonewton. Once we reach the point C, 5 kilonewton is acting downward. So already you have plus 11 at C. So 11 minus 5. 6 kilonewton is the shear force at C. Now, for example, let us proceed from right hand side to complete the diagram. Okay, so RB from right hand side upward is negative. So 22 kilonewton shear force negative. Then similarly D to B you have a UDL. Already you have minus 22. UDL is acting downward, so it is positive. So minus 22 plus 2 into run length 1. Okay, so you get 2 into 1, it is nothing but 2 into 1, 2 into 1, it's 2. So 20 kilonewton you have here. Okay, and once we reach the point D, 20 kilonewton is acting downward. Okay, so now we are proceeding from right hand side. We are proceeding from right hand side. So from the right hand side means downward is positive. So plus 20 point load. Already you have minus 20 shear force at D. So plus 20 minus 20, the shear force is 0. Now you just simply connect the shear force values between C and D by a straight line, and it is understood that the nature of the shear force diagram for UDL is an inclined line or triangular lines. That's it. There ends the shear force diagram for the given loading. Okay, so here the shear force is 0. Okay, now let us plot the bending moment diagram. Okay, so we know that the bending moment at A and B are 0. Okay, 0. How to find the bending moment at C? How to find the bending moment at C? So bending moment at C, okay, 13 into 1. We are proceeding from left hand side, clockwise positive, anti-clockwise negative. 13 into 1 minus 2 into 1 into 0.5. That is nothing but 12 kilonewton meter is the bending moment value at C. And the nature of the bending moment is, bending moment diagram is a parabola because of UDL. Okay. So now bending moment at D, you will just proceed from right hand side, 22 into 1, right hand side anti-clockwise positive, clockwise negative. So 22 into 1 minus 2 into 1 into 0.5, which is nothing but 21 kilonewton meter is the bending moment at D. Okay, again this is a parabola. Okay, so at D we know that the shear force is 0 and 21 kilonewton meter is the bending moment value at D, which is the maximum bending moment. And between C and D, it's a parabola. Just connect these two values, that is 12 kilonewton meter and 21 kilonewton meter by means of a parabola. Okay. So this is the bending moment diagram for the given loading. Thank you.